Okay, as I was saying before, you can find on the e-learning a revisited script of last lesson because the model we created was not so performing for some reasons. And so you find, well, the original one that we wrote during the lesson, which is called lesson 16. And then there's also lesson 16 reloaded that has almost the same model, actually. I think I just gave a longer time span of the data, a better organized and commented script, and better predictions. So starting from today, so we have including today, 3 lessons. We're going to deal with the problem of machine learning for forecasting. I assume that machine learning algorithms you already know. I mean, you've been doing that for more than 1 year. So I will not explain, of course, the algorithms from scratch. In case some of you, maybe Erasmus students, are not acquainted with machine learning models, I'm writing down this thing that you see here. As soon as it's ready, I mean, it's already very long. I wrote it during the weekend. I'll be publishing that on the e-learning. There are some like introduction to the basic algorithms in machine learning, and so yeah, you should be also able to at least have a source where to find this information. So let's just start with defining what a machine learning algorithm does. So basically, a machine learning algorithm is, at least we will deal just with the regression problem, so no classification problem. Why? Well, because time series are usually numbers. Of course, we could also have like a time series of labels or categorical variables, as you want to call them. But in this course, we dealt mostly with only with the numeric time series. So you can see a machine learning model as a model that tries to fit this kind of relationship. So we have like an observable, so the target variable yt, which is an unknown function of some, as a statistician, I usually call them regressors, but in machine learning, they're often called features, or they have many names. So in statistics, they already have many names. You can call them regressors, predictors, covariates, and so on. But in machine learning, those 3 names were not enough, so they added the name of features. Anyway, I will be calling it usually regressors or variable anyway. So we assume that in our case, the time series yt is a known function, and possibly non-linear function of some xt variables. Usually yt is just one variable and xt is a vector of variables, but that will be clear later. Something yt could even be a vector, okay? But let's start from the simple case. Yt is a scalar, xt is a vector, and of course, this relationship is observed with some noise epsilon, okay? And the noise is usually assumed to have 0 mean, okay? And an equivalent representation of this is the one on the right, is saying just the expectation of yt given xt, assuming that epsilon t has expectation 0, then if I take the expectation conditional xt of yt, I just obtain f of xt. So saying that we have this kind of model with 0 mean epsilon, or saying that we are trying to find a model for the conditional mean of yt given xt, is just the same thing, okay? So we're building models for not only estimating usually when we go with linear regression, f is just a linear function. So we know that function. And we just have to estimate some parameters of that function. But in machine learning, we're in the condition that usually in statistics is called non-parametric regression. Non-parametric regression means I don't know f. So I have to estimate the whole function f, not just some parameters of a known function, okay? And machine learning basically does that, tries to estimate this f, okay? So all the different algorithms are just ways to estimate this f, okay? Of course, you can see it in a slightly different, but actually more general way. I mean, machine learning algorithms, what the machine learning algorithms do is they try to minimize some loss function that, for example, if it's quadratic, you know, from our lessons at the beginning of this course, we get, in that case, we get the conditional expectation. In some other, if I use other functions than the quadratic loss function, I may get different value. So that's why I say it's more general than this one. Here we're just talking about the conditional expectation. We want to estimate the conditional expectation of yt given xt as a function of xt, of course. Here, I'm not saying we want explicitly the conditional expectation. We may want other type of predictors that minimize other type of loss functions. So I put here the problem more in general. But of course, if this L loss function is quadratic, then this problem is equivalent to this up here, okay? So this is usually how machine learning algorithms are organized. So you have some kind of loss function. Usually you pick the quadratic loss function if you have numeric data, but you don't have to. I mean, there are also other kind of loss function, as we already saw. And you want to find the function g that usually belongs to some given class, which I called f, so this calligraphic f, that on the average, so if you pass or the loss function on all your data minimizes your loss, okay? So this is basically a machine learning algorithm in a nutshell. That's what it does. I don't know if you've ever seen it this way, but this is just what a machine learning algorithm is. So it's a non-parametric way to estimate G. And how do we estimate G? Well, the class of the function G is determined by the algorithm you're choosing. So this f, so this calligraphic f, to which G belongs, is the machine learning algorithm you chose to work with. So for example, if you choose like trees, so those functions are just piecewise constant functions, for example. So if you choose neural network, typically you have like nonlinear transformation or linear combination of the time series which are, or the variable which are contained in xt, and this nonlinear function have like, it's usually linear combination, and then you take sigmoid or the ReLU kind of activation function. So you're defining, so your machine learning class of algorithm is defining the class f of function within you're looking at for the best G, okay? So, but at the end of the day, you're just trying to minimize this loss function, choosing between the G that belong to the class of machine learning algorithms you're interested in, okay? So this is basically what machine learning does. And as I tried to explain you at the beginning of this course, changing the loss function changes what you're doing. Often we will be using the quadratic function, so conditional expectation is what we are trying to estimate. But in some real problems, you may want different kind of loss function, and in that case, you will be doing something different than this, okay? It will be different than this, and you can still represent it this way, but of course the epsilon will not be a mean zero variable, will usually have some form. You can always map this to this, but I mean, the easiest way is when L is just the square loss function, okay? This is what basically a machine learning algorithm does. And here are some example of alternative loss function that we already discussed at the beginning. So the absolute value will give you, for example, that you're predicting with the conditional median. If you use the so-called pinball loss function, then you get the quantiles. So you can actually do much more than just use the conditional mean. Sometimes you want to have a better vision of future value. We'll be using this for forecasting. So sometimes we want to rebuild the whole distribution of possible future observations. And in that case, maybe you may want to have many machine learning models that correspond to different quantiles. Because if you estimate many quantiles, at the end of the day, you kind of have the whole distribution of your future observation. So if you're interested in the whole distribution of future observation, then quantiles, so the pinball loss function, are good ideas, okay? But anyway, let's just go standard. I mean, you've been probably just minimizing square loss function, so mean square error. Well, this is the usual plot that you already saw. I'm trying to put in these notes as much as I can. So for example, we were just mentioning, well, this is the class of function, for example, that trees allow. So they're just piecewise constant function on subset of the space of the range, or the whatever you want to call it, of X, okay? Of the support of X. And here, in some way, we're minimizing square loss function when we apply that as a regression tree. So, I mean, I will not spend time here because I assume you know all these things. And if you don't know or you want to review them, of course, I've written much of this. And I think that probably you haven't seen in many other places. I tried to generate some few, actually about 30, artificial observation. This is just a cosine with some noise. So you observe the blue dots, but the real f is the cosine function that you see here. And then, of course, if you use like, well, this is a overfitting tree. And of course, the overfitting tree will pass through all the points. But if you prune the tree, actually here we get a very small tree. And this is like the tree approximation of the sine function, which is very bad. But anyway, we know that trees are not, a tree alone is not a very good predictor usually, especially of continuous functions. I added this class. I don't know, probably you've already seen it. You can do like your standard regression trees, but then at the end of the nodes, so the end nodes, you can actually do a linear regression just inside that node because you have the X and you have the Ys. And if you do that, of course, you fit the data more, but you can also build functions that are not piecewise constant, but they're piecewise linear. I don't know if have you ever seen that in some courses? They're called linear regression trees. So the only change with respect to the standard tree is that you get to the final node. In the final node, you have, I don't know, 30 observations. And then you regress those 30 observations, the Ys on the axis using just linear regression. Of course, you have to keep the tree in a such way that it contains at least so many observations so that you can fit a linear regression, because otherwise it's a problem. But then, for example, for this very, so I found this package in R that does that, and it finds just two nodes, but the two nodes are actually very good here. Look at it. It finds just two straight line, and they're not bad for a sine function. I don't know why this happens, but they're just two straight. Maybe just because I have a point here and a point here. Well, they should join somewhere here. Okay. Yeah, this is just an extension of regression trees. Then I have, of course, cover random forests, which of course are doing somewhat better. And I cover boosted trees. Here I also have, I always compare, the root mean square error, because here we know the real function, so I can compute the root mean square error with respect to the real function. So for example, here, random forests are doing the best, but also linear regression trees are doing good. Of course, the regression tree is terrible. Here, there are also some real data examples. So yeah, here show you probably what you already know as variable importance. Yeah, boosted trees. So I just cover very standard things. Boosted trees are also doing very fine, and indeed, yeah, they're also close to random forest and to linear regression trees. Then I cover a k-nearest neighbor. K-nearest neighbor is kind of different. It's not really a model. It's just the model are the data. You know, k-nearest neighbor. Okay, so of course we can use that for forecasting as well. We will see how. And again, well, here I tried various k's value. So just 2 neighbors, 4 neighbors, 8 neighbors. It looks like the 4 neighbor is the best one, and indeed, it's the one that is doing the best up to now. And then I also explain a little bit like shallow neural network, the difference between shallow and network and deep learning. And here, well, neural network is doing really well. It's just a simple neural network with 1 layer with 5 nodes, and it's doing the best of all those. Okay, so that was not a point of the lesson. That was just show you what I'm, well, if there was something new, that the linear regression trees, that's good. Okay, so let's go to our problem. So, you know, all these algorithms, how can we use them to forecast? In order to forecast, we have few problems or a few issues maybe that we should deal with and understand. Some are common to all machine learning algorithms, are just associated with some of these algorithms. So first of all, what are the features or the predictors or the regressor, whatever you want to call it, that we can use in a forecasting model? So we have a past and we want to predict the future. Of course, we can use lagged value of the target variable, so lagged values of the y's. But of course, it depends how many lags, or starting from what lag to what lag I should use. Well, I may have some problem in that, because if I want to predict h steps ahead, I don't have for example, the last lag of the observation. If I try to predict yt plus h, I don't have the yt plus h minus 1 observation. Okay, so in that case, I wouldn't be able to have the information that I want to predict if I put, for example, 1 lag of the time series in my model. So if I put 1 lag of my time series in my model, I'm just able to predict 1 step ahead. We will see how to solve this problem. This is just the issue. There are, of course, ways to solve this issue. But so if you just think about that problem, if you want to predict, like, this is how we call the prediction. Well, we did the same with ARIMA and UCN. So for example, this is the h steps ahead prediction based on information up to time t. But the information up to time t is only all the y's up to time t. So I cannot have it in this model, the just lag 1 information, because it's not present. I should have the t plus h minus 1 y in my set of predictors, which I don't have because my time series is ending at yt. Is that clear? So this is an issue. If I just do one step ahead prediction, there is no problem. I just lag one and more than once my time series. But if I want to predict h steps ahead, then I have to remember I will have just the information up to time t. So I have to put at least h logs and more of my time series if I want to use it. Okay, so this is the first problem. So of course I can use lagged variables, and we will be using lagged variables, but we have to deal with that. And then, of course, and this is very important, because sometimes I see many students, but not only students, that say, okay, I want to use machine learning for forecasting. I just put an whole bunch of all the information, so all the y's in my model, and that's it. Actually, apart from the fact that sometimes you have some features or regressors that are important, like, for example, if you want to predict electricity demand and you have information about the temperature or, I don't know, other variables that are relevant for the consumption of electricity, you might want to use them. But of course, you can put only so-called, I call them predictable regressors. So regressors that in the future are known without error. So for example, the temperature is not really there. You can only put lagged temperature, for example. So what kind of regressor have this characteristic? Well, the artificial regressors. We'll be using artificial regression all the time. We used linear trends or quadratic trends. We used dummy variables, especially for the seasonality. We used sinusoids, again, especially for the seasonalities and so on. Okay, so all those variables are relevant. Maybe they're not the same variables we would use in linear models. So in linear models, we saw the dummy variables and sinusoids, also splines, could be good idea. We will see that in machine learning algorithms, we can provide the same type of information. So what's the type of information, for example, we have to pass if we want to model seasonalities? Well, just the periodicity. Seasonality is something that is periodic. Okay. Of course, a machine learning model, if you put enough past data, will eventually learn that periodicity. But you need so many observations that usually in time series analysis you don't have. I think I mentioned to you already that if you want a good machine learning algorithms, like a very complex deep learning neural network, okay, to learn the Eastern algorithm, probably you need 400 years of data, okay, because it's not so simple to just look at the time series and say, oh, okay, the rule for the Easter vacation is this one. It's not so straightforward. It's a strange function that is not simple to estimate. Okay, so it's a good thing if you help your machine learning model to learn things that you already know that are present in the data, exactly as in linear models. Don't think that machine learning is just automatic. It's not that way, even though many try to pass that information. You can help that algorithm to learn the things that you know are present in the data. And so we will be using many, actually, artificial regressor or predictable regressor. Of course, they also have the advantage that if they're completely predictable in the future, you can produce h steps ahead prediction or forecasts, whatever h is, okay? Because they're known in the future. So you don't have this problem that we have with the lagged variables. And of course, actually, we will be doing both things. We will be building forecasting models using machine learning, both with artificial regressors and lagged target variables. So that's basically the recipe we'll be using. But artificial regressors will be built usually differently than what we did in linear models, especially if you have like tree-based algorithm in machine learning, because tree-based are very far away from being continuous. They are very, they are piecewise continuous. So they're piecewise constant. So they're very jumpy. They jump up and down. So something like a cosine function is a very bad feature to pass to a tree-based method. Okay. So we can kind of think in our head. There are some methods in machine learning that tend to preserve like continuity. Like, for example, neural networks, they tend to be continuous. It depends, of course, on the choice of the activation function, but usually you choose continuous activation function, also because of the gradient-based method of training them. So we want derivatives, so they have to be smooth. Also, support vector machine. Actually, support vector machine, if you remember, they start just from a linear regression, and then they go outside of the linearity using the so-called kernel trick. So the kernel trick takes you out of the linearity, so bring you in a larger space, but it's at the end of the day is usually a space of continuous functions. Okay, so for example, cosine and sine function could be still good if you use some kind of neural networks and support vector machine, but they are probably very bad on all methods based on trees, okay? Because those are jumpy. And that's the first issue. Well, here just explain what dummy variables are, and central dummy variable and sinusoids, all these things we already seen. But actually, the most useful way to communicate to the machine learning model the presence of seasonality is usually just accounting the counting of the period without the year. So, for example, for the within day seasonality, suppose we have an hourly time series. So we just provide as an information just the number of the hour of the day. So from 1 to 24, and then it repeats itself. It's already a good information for the machine learning model because it knows there is something that tends to repeat every 24 hours. Okay. And the same thing within week seasonality. You can just tell the number of the day, also the name of the day. Anyway, the name of the day will transform into numbers. So you can just build the number of the days, so from 1 to 7. And again, you are just communicating to the algorithm that there is this kind of periodicity, okay? And so you're helping the model learning these periodicities. And for example, you can do also the same thing with the year within the day within the year. So a counter. So the first one is the counter for 1 to 24 hours. The second one is just a counter either for 1 to 7 days, or you could even put from 1 to 168 hours. But usually it's better to use the same way we're used to reason about that. So I would just associate build the number of the weekdays. So, and usually actually it's better to use the continental way, not the US way. You know, US way of counting starts from Sundays and end up on Saturday. Actually, since the weekend are usually similar between them and the work days are similar among them, it's better to use the continental way. So starting from Monday, because in a regression tree, then probably just one cut between the working days and the weekend will do the job. Okay, that's just a small suggestion. Of course, it's not really that important, but I mean, if you reason something, there is a better way to provide the information to the machine learning algorithm. And the same thing as I told you, within year seasonality, we just can. You could even name or number the month, but the month generates jumps in just when the month changes, and that's probably not the best choice for choosing the change. So just provide the number of the days, or a number between 1 and 366 at the end of the day. Okay, so that's already a lot of information for the machine learning model to learn from. So those are important. What about the trend? Well, the trend is actually can be a problem. Why I mentioned the trend, because when we started with linear models, we said, okay, we have a trend, we have seasonality, let's deal with them. The trend is a little bit more tricky in many machine learning algorithms, and we will see why, and we will see how to solve the problem as well. And then we have the second or third issue, well, the second issue. So how to build the features, and the second issue would be how do I do multiple steps forecasts? We just mentioned a problem. If I want to predict 8 steps ahead, I cannot have one leg of my time series because it's an information that I don't have at 8 steps ahead. So suppose I want to build a model of this type. So it's a model where YT is just regressed nonlinearly on its own past. And suppose we want to predict 8 steps ahead. Well, there are many. There are basically, well, 3 solutions. 2 are common to all machine learning models. The third one is just you can use just for certain machine learning models. So the first solution is recursive forecast. And the idea is stolen from the linear model, even though in the linear model world, this is the optimal way to do forecast. In nonlinear models, this is not optimal. So we say that, of course, the one step ahead prediction you can do because you have the last information in your information set. But when you move to T+2, the idea is that instead of, you don't have the information at T+1, so instead of using the information at T+1, I generated the forecast, I put it here. Okay. Of course, you're no more predicting the condition with the conditional expectation, because as I already told you at the beginning of this course, if a nonlinear function of the conditional expectation is not equal to the expectation of the nonlinear function. That only holds for linear models. So if f is linear, this is the optimal way to do the prediction. If f is nonlinear in machine learning models, it's never linear. Then this is an approximation. In machine learning books coming from from computer science, they will underline the fact that you're accumulating errors. And that's a way to see it, because of course this is not the real one, it's a prediction, so it's a noisy version of the yt+1, and of course so you're accumulating all those errors. But I mean, accumulating errors happens also if you have a linear model. If I put a linear model here, I'm still accumulating errors, but the prediction would be anyway conditional expectation, so it will be the best you can do. So it's really not a problem of accumulating errors. That's a universal problem. If you forecast many steps ahead, you're accumulating many shocks. So all the models are accumulating errors. So it's really not the issue. That's written in machine learning books, but it's really not that problem. Any forecast in many steps in the future will accumulate many errors you're making, of course. The problem is that you're predicting with something which you don't know exactly what it is, what kind of loss function is minimizing. We are no more minimizing the square loss function. I don't know. And sometimes there may be another problem. You may observe like exploding forecasts. This is very common, for example, when you use neural networks, because since you are building very complex function of the future with respect to the past. For example, assume you have like estimated for some strange reason a linear model, but that linear model has a root that is inside the unit circle. If you remember what we said about that, that kind of processes just explode very quickly, okay? And this can happen because we have no control. While in a linear model, we can check the roots of the characteristic polynomial and say, okay, this is a stable, or this is a unit root, this is explosive, I cannot use it. Okay, here we don't know exactly what kind of process we're generating, what kind of recursion we are generating. So sometimes, this is especially true for neural networks, you may see that your forecast, maybe the one step ahead forecast is fine, the two steps ahead forecast is still good, but then it starts exploding with, and it goes to values that are really not possible in real life, okay? So this is another problem related to using this recursive forecast, okay? What's another solution? Well, this is called recursive forecast. Another solution is the so-called direct forecast. So actually, I don't build one model, I build 8 different models. So I build one model for one step ahead predictions, where I have y of t, of course. I build a model for 2 steps ahead prediction, and I still have as a last observation yt, and so on. So this is direct forecast. So you don't build just one model, you build so many models as your forecast horizon. This is fine, of course, if h is not too large. If h is very large, it's something you don't even have enough data to build it, to train that model. But this is an alternative, and in principle, this would give better result. Also, because in some way here you're doing exactly the same thing, because yt is also just, y hat t plus 1 even t is just a function of yt. So actually here you have just data from yt. What it's changing is just the shape of this function f in some way. But here it changes in an unknown way because you're applying the same f, but here you have already applied f. So it's changing in an unknown way. Here you have actually different functions. Maybe I should have used different symbols here, maybe f1, f2. So here you're estimating actually different functions every time. And it's always the optimal function in some way. So this should be better than the other one. Okay. The other one is simpler because you estimate just one model and then recursively you apply.
Do you recommend not using neural networks for our assignment because it's maybe
no
too much, or?
No, I mean the data. I think I gave you a relatively high frequency, long time series. So probably in that time series, neural network could do well. Not too complex, of course. You cannot have thousands of parameters, of course, but maybe a few hundreds you can manage. And then, of course, in neural networks, at the beginning of this world, there were not so many so-called regularization methods. Now, it's well known that, especially if you don't have many observations, you have to regularize your neural network. So you probably know the so-called weight decay, which is just the ridge regression correction. You know the dropout layers. You know, layers where you randomly just put to zero some neurons. So there are ways to control the complexity of the neural network if you don't have so many observations. So my suggestion, you can try either not complex neural network, but if you go with more complex one like LSTM, which they are used for forecasting, okay? So LSTM grew networks, you can use them, but then of course keep in mind you want to regularize them. So maybe put some dropout layers, some strong penalization using the weight decay, okay? Maybe one network you should try it. I mean, we also see in the example, they do work well. But anyway, in neural network, we have another solution. So this is the second solution to the multi-step forecast, but neural network, they do have another possibility. Because if your algorithm is multi-output, so it manages not just one target variable, but multiple target variables. And this is true for neural network. And it's true also for example, for KNN. Then in that case, instead of having just one y to predict, we have a vector of y's. And of course, we can define our vector of y's this way. So we put one step in the future, two steps in the future, until each steps in the future. And this has to depend, this is as you see, I used a bold F, a letter to represent that this is actually, this returns a vector of values, okay? Not just a scalar of values. And this is also the epsilon, of course, is a vector of errors or zero mean errors. But you're building like a neural network where you're not just predicting one step ahead, but you're predicting from 1 to 8 steps ahead. And is this a good idea? Usually it's a good idea because usually information is used more efficiently in this way. You may think this, some of you probably use like the autoencoders, you know the autoencoders. Like autoencoders are just, autoencoder has this structure. You have like many features as an input, so many variables. Then the network goes like, gets smaller, gets to very few neurons in the middle, and then you try to rebuild the same information starting from few neurons, okay? In some way, you can see in a similar way, it's like here you have many outputs, and here you have many inputs. Of course, they are not the same variable. It's the same variable, but lagged. But usually, you can like summarize all the information contained in the past of the time series into few neurons that contain the real important information about the past. And then these few neurons will give you the right prediction, one step ahead, two steps ahead, 8 steps ahead. You can, for example, build this type of network. For example, in the linear counterpart of this that I just described, I don't know if you ever came across into, it's called reduced rank regression. I don't know if you ever heard it. Also, think this is a multivariate regression problem. So you have many y's and many x's. And so if this was a linear model, you would have like a matrix that multiplies all these x's, okay, to get all these y's, okay. If the matrix is full rank, okay, you have to estimate many parameters, and that's the normal multivariate regression in some way. But assume that the regression matrix that you have is of rank smaller than the full rank. You can see that as taking some linear combination of the x's that are the relevant linear combination of the x's to predict the y's. And then you project the y's on those few linear combination of the x's. It's just the same thing. So if f is linear, your similar autoencoder, it's not really an autoencoder because we don't have on the left and on the right hand side the same object, but we have similar object, okay? So in linear modeling, it would be the so-called reduced rank regression. And in using neural network, it would be something that has the same structure as the autoencoder, but it's not autoencoder just because we have different things on the left and on the right hand side, okay? But that could be a good strategy, for example, with neural network. So like, I take a lot of information from the past, then I just take few non-linear transformation of this information of the past, because this few non-linear transformation will be the influential one for the future. It's like a hidden factor in some ways, a hidden factor that you're assuming is moving many time series or the whole pace of the time series. So as I told you, this is in my mind, this is just possible with with neural network, but also with KNN. KNN, we will see how to use KNN for forecasting. Then let's go to the next problem. Range limitation and the presence of trends. So we saw that many time series, they do have trends. So they trend to grow up or go down. And this cannot be reproduced by many machine learning models because here's a list. So all the tree-based methods, they can reproduce only what they have been trained to, okay? Because, I mean, a tree just take subgroups of the data, so classify the subgroups in different final nodes, and then take averages of this data. So you cannot like extrapolate trends by just taking average of past data. Okay, so trees and all the methods that use trees cannot predict outside the range they have observed. The same holds for KNN. We will see a little bit how the KNN can be used for time series forecasting, but KNN, again, what are we doing with KNN? We look like at past-wise, we look usually at a situation that is similar to the one I'm observing today. So for example, I'm observing the last few observations of a time series. I want to predict the future. I try to look in the past to situations that are close to the one that I'm dealing with. I take maybe the three situations that are the closest, and I see how the future goes with respect to the three closest situations. And I just take averages of past information as well. Okay, so again, I'm grouping past information and taking averages over the Ys in this past time series. So again, KNN is not able to go outside the range that have been observed. What about neural networks? Well, neural networks are, we don't have a unique answer here. It depends. If you go back to your use of neural networks, what you usually do, for example, you constrain all your data to be between 0 and 1. That's a typical thing you do before doing neural networks. So I take the minimum, the max, and I rescale my data so that whatever Y I have, this Y will be between 0 and 1. And usually 0 and 1 are contained, so the smallest value will be 0, and the largest value in your sample, in your training sample, will be 1. Okay. Again, if I use sigmoid activation functions, so let's say between 0 and 1, why do we do that in neural network? Exactly because neural networks were born especially on sigmoid activation function. Okay. So you inject 0, 1 variable that get transformed and remain between 0 and 1. Then you have another layer maybe, and this 0, 1 get inside other sigmoid function, and that also stay between 0 and 1. Of course, then I will give you again the same metrics as the original data by anti-transforming. But of course, if I have a trend, probably my 1 will be the last information, the last observation. And I'm not really able to exceed 1 unless there are a couple of unless. If I use sigmoid function, I could maybe constrain the data to be not between 0 and 1, but in a shorter range. So for example, if I constrain the data to be between 0.2 and 0.8, then there is some more space on the top and on the bottom to like predict trends. So I could, I mean, in neural network, I can work a little bit on the network itself to be able to go outside a fixed range. And even better, if you use the ReLU activation function, the ReLU activation function is first 0 and then just a straight line. Well, a straight line is unbounded, so we don't have that problem. So if we use ReLU activation functions, well, neural networks can also work on trending data. So neural networks are more flexible as far as that. Tree-based, no, we have to find a solution for that. KNN, again, we also have to find a solution for that. Okay, you see there are many things you have to consider when you do forecast that you're not used to consider when you do just like cross-sectional prediction, okay? So here's an example on the famous air passengers. I mean, everybody knows that. So we're just trying, whatever the machine learning model is, I'm just trying to fit this model. We have like 1 year of lag. So we can predict up to 12 steps ahead without problems here. And XT is just the number of the month, okay? So the month number. Let's see what happens. Here I use trees, random forest, which are still trees. I use KNN, and I use a simple neural network. Actually, I use two neural networks, one based on a sigmoid activation function, and one is based on a ReLU. It's not a ReLU, it's something that is an approximation to a ReLU. It's called the soft, I don't know. Well, this is it. So maybe you remember I don't know. In some way, it's just a ReLU where you just make differentiable the point where it's not differentiable. So it's a gradual way to get to the linear. But anyway, so I do all of these things here. As you see, the model is always the same. And in R is nice because you see these things. When you use formulas, you're predicting using the same thing. And here is the results. So this is I'm predicting the last year, and this is just to show you that it's increasing. I mean, I included that. So first of all, let's go where the tree is. So the tree is the lila or pink, and of course it's not great, but as you can see, it's much below. It's even below this top thing here. So, but we know that it cannot exceed the range in which it was fit. Even if I go to random forest, which is the blue one, yeah, the blue one is catching the seasonality very well, but it's not catching the trend at all. It's not possible. It's really not possible. It just can reproduce the range seen in past. What about KNN? KNN is the red one. Again, same problem. It's catching the seasonality in a decent way, but the trend is really not able. I was surprised that the sigmoid based, which is like the light green color, neural network is actually doing well, even better than the ReLU. And probably it's just that inside the network it never reaches the extreme 0 and 1. So, and actually neural networks in this one are, you just have to watch out. Sometimes they will just work. But with ReLU, of course, also in theory, I have no problems. In this case, for some reason, I don't have problems also with the sigmoid, okay? And they, of course, catch the seasonality very well. So they're doing an excellent job. What are the solutions? Well, the simple solution usually is, as we're used, I mean, in ARIMA models, we've been doing that all of the time, is working on differences. You know, if we have a trending time series, probably the difference of the time series will not be trending anymore. The first difference could be could be also seasonal difference. I call this the first difference zeta t and the seasonal difference wt. But anyway, and how do we build then the prediction? Well, we just have to accumulate all. Of course, we're predicting the increment. And so in order to predict the increment, I have to know the initial value with respect to which I have to increment. And then I add every increment. So the h steps ahead prediction are just the last available observations plus how many increments I have to add in order to reach that horizon, okay? Or of course, if you have some kind of seasonal difference, the same thing applies, but then you have to start from S lags, because the last observation is not This one is the one of last year, okay? So you start from like last year observation plus 1, and then you add your, let's say, yearly increments, okay? So this is how you solve usually this problem. For example, in KNN, usually something different is done. There is a nice package in R that implements that. And maybe we can talk a little bit about KNN. We'll just pause that for a moment. We just go through the last issue, which is cross-validation, and then try to reason on some of the specific things. What about cross-validation? You know, cross-validation, usually all these models have tuning parameters that you fix by looking on the grid of these tuning parameters using cross-validation. So what's cross-validation? Usually you just take your training sample, you partition in I don't know, K, let's say, K groups, usually of equal size, and then you train the model without each group and try to predict that group, and then you summarize in some way the loss function that you compute on those groups. Fine. That's cross-validation. In some way, you could even do it with time series data, but it's usually not a good idea. Of course, in time series, we have the time direction, and that time direction is important. We cannot fake it. There is not a direction in time, okay? So usually cross-validation is done in a different way. Well, I summarize it here. So usually you start from maybe half of the sample, you train your model on half of the sample, and you do your 1 step ahead prediction, 2 steps ahead prediction, whatever you want, each steps ahead prediction, okay? So we start from half of the model, and then you do your 1, 2, 3 steps ahead prediction. Then you add the next observation, and you have 2 choices. You can either just use the trained model to predict the next 3 observations, for example, or retrain the model and then do the prediction. Of course, in principle, retraining the model should be the better way to do that. But of course, we're adding 1 observation at a time. And if you have many observations, that can be really time-consuming, retraining every new observation, okay? So sometimes you prefer to retrain every, I don't know, 100 observation. And so also because anyway, retraining with just 1 more observation doesn't change much the model. But if you have like 20 more observation, maybe the new model would be different from the previous one. So you have this to take this choice. You either add a new observation, retrain, and do the prediction, or you do the prediction for a few iteration, and then you retrain the model every, I don't know, 100 iteration or whatever you want to try. There are also papers that cover that. There's also a PhD student in our PhD that is trying to see how often it's a good idea to go with this retraining in typical forecasting problem, okay? But here I used Gemini to produce these fantastic pictures. I mean, it's great. I just described the picture I wanted to have, and I have the picture. I don't know if it's stolen from some books. I'm not sure, because you never know. Today, you know, I have received an email from Perplexity. I didn't know anything about that. Says that there was a lawsuit because Perplexity trained its large language models on stolen books and articles. And the judge, well, they came to an agreement, and they will pay up to $3,000 for every book that was present in that list of and my book was there. So, well, I get only 10% of the sold, not on the I mean, the PDF of the university, I don't get any credit for, but for the real copies sold, I get 10%. So I had to write down, I get 10% on. So maybe I will get 300 euros just because Perplexity trained on stolen books. If they were not stolen, probably there was no problem. So I'm not sure if this was stolen. I use Gemini, so Gemini is not But correct. But it's funny because I did this yesterday and this morning I received that email. Anyway, I hope it was not stolen from any books. It's a genuine production. So this is just a way to see this. So the first iteration, I start like alpha percent, like 50% of the train step. Then I do my 1, 2, 3, for example, step ahead prediction, and I store them in some way. And then I add a new observation. Actually, here's adding two. Anyway, I can either just do the prediction or also retrain the model. Here it just says retrain and update forecast. Retrain in some ways is optional. You can retrain just sometimes, and so on. Okay, another here we have this situation where actually we're changing the length of the data set. Here we start with a smaller data set, and in the end we have a longer training data set, which is fine, I mean. But you could also have an alternative where you have like a rolling window, just to keep the train set always of the same size. So just instead of recursive, the other one is called recursive cross-validation approach, and this is a rolling window cross-validation approach. And of course, then you just take the mean square error, for example, of all one step ahead prediction. Then separately, you do the mean square error of the 2 steps ahead prediction, 3 steps ahead prediction, and so on. So you also have an idea of the errors you're going to make by different forecast horizon. But with Sdmtsa, you may see that there is one model that is better for short-term prediction because you see the H1 and the H2 are the best, but then you need another model, different model for long-range forecasting. Okay, there is no rule that the best short-range forecasting model is also the best one for long-range. Okay, and actually it understood because it reproduces all this information. Okay, well then I start, this is just a starting point. We will be doing all these things now on the electricity load time series because it's hourly, it has many strong seasonalities. So it's a nice example where to apply all of these things. It's long enough, I think. I have data starting from 2017, but actually I could have data starting from 2004, so they're just there. So, for example, maybe something that has to be re-explained, and then I'll tell you how the trend problem is solved, is the KNN, as I was anticipating before. So how do we use KNN in time series for forecasting? I mean, KNN is not bad for forecasting. So we have our time series, and let's make it trending. Let's make it kind of like the air passengers. Okay. So the first thing you have to decide is how many subsequent observations you want to use to compute the closeness of the observation. So let's call P like the number of subsequent time observations to consider to measure the distance. 1 point, we could use just the past of the time series again, Or we could use the past of the same time series and additional other features, or additional other regression. Okay. Now I'm just speaking about the past of the time series. Of course, I could add other regressors. Remember that in that case, I mean, here we kind of have all the time series is in the same unit of measurement because it's just one time series. If you add regressors, KNN of course is sensible to unit of measurement. So usually you have to standardize everything or include everything between 0 and 1. Okay. But let's just now assume you want just to look at the past of the time series and no other regressors. So it means that I will, so for example, we're at the end of this time series. So the sample we're interested in is maybe this last part here. These are like the last P observation. Okay. And we want to compare this with any other vector of subsequent observation of the time series. So I have to compare this with, well, it's just like a moving sequence. So for example, I want to compare it with this one. So these are the first P, and then I want to compare it. I just changing color with this one up to here, and then so on until I compare the whole time series to the specimen I have that at the end. So then I compare this. So I just compare this. So I take the distance between the last part of the time series, which is the one I can use to predict, and all the rest of the time series, same length of vector, subsequent observations. And then, of course, I order all these vectors, so this subset of the time series, by the distance. You know, I have to pick up a distance. Usually I use the Euclidean distance, but you can use any kind of distance. And you order the chunks of this time series according to how close are to the red specimen you're using, okay? And then the K, of course, determines how many of these closest samples are being used for forecasting. So suppose, I mean, in this case, this is a trending time series, and here you see the problem with the trend. Of course, the closest ones are the last ones, okay? Because these are very small and they're very high. So if I just compare the distance, I mean, I will just select probably the last few observations here. But then what I do, I look at the future, and of course the horizon matter here with respect to the selected pieces of time series. And then I just take the mean or the one step ahead subsequent observation of the, let's say, 3 samples that I selected. So again, I can actually, if I want to predict, for example, H steps ahead, and H, for example, is larger than P, then I can only look in some way to, this is H long. I can only look backwards here because otherwise I don't have enough future to do the prediction. Okay, so I select this the similar, so the more similar 3 sample path. So one is the black one. I say I supposing that we are setting k equal to 3. Of course, it's k is not equal to 3. You have the right number of sample path. And then I have this. So these are like the 3 sample paths I selected from the past that look whose distance is the closest to the red line. And then I just take the future with respect to this. Maybe I just use the same color here. So I use the future of this, I use the future of this, I use the future of this, and of course I take the mean like vertically, okay? So the mean of these 3 will be the prediction of 1 step ahead prediction. So I take the means here. You know, it's clear that we have a large problem. In this case, I drew such a time series to show you that we have a big problem. So the big problem is probably I just picking this 3 that I picked will be just very close to the end of the time series, and probably the prediction will be bad because they will be all underestimating the future because I'm taking the mean of something that I know is smaller than the future, actually, because the future is trending. So how do we solve this problem? Of course, one solution I already told you, we can work on the difference of the time series, and that would work. But for example, something that was suggested by the authors of this package that is present in R, I will copy the, I think probably the paper is ready on the e-learning. I have to check. If it's not on the e-learning, I will provide it to you. They suggest to do a different thing. So to preserve the trend, they say, okay, instead of looking at the distance of the real values, we demean the values. So so if I'm, instead of looking at, try to draw the thing and then we reason on the new draw. Okay, instead of looking at these values here, maybe these values, I don't know, here, compare, I take the difference between the values and the means, okay, here and here, okay? So I kind of compare not the level of the data, but just the movement around the mean, okay? So I'm comparing things that are on the same level. The level is 0, the average level, because I'm taking off the mean, okay? And that's the way you select the closest sample. But you still have the problem that you have to predict something that is growing. And the idea is that you take also you take off this mean also from the future values. So instead of, again, of getting this value, you take off the mean also from this value. So the future value that I want to use, you predict them, and then you add the mean. And that you can do here. So because we have a new mean here, we are stealing the mean version of the future with respect to this specimen here. And then I add the mean of this data. Okay, I can add or I can multiply by the mean. There are these 2 possible destinies, okay? I may just or take off the mean or divide by the mean. One is more for multiplicative time series, and the other one for additive time series. For example, for air passengers, it would be better to divide by the mean. So I don't know if I explain myself well. So I take first of all, for any specimens that probably will look like this, and also the one we want to compare to, that something in IT it's called the query. This is something called the query. But this is, let's say, the last part of the time series. We have to compare all the other parts of the time series too. The first thing I do is I demean. So this is like here, like this, like a mean 100. Okay, I just take off a 100, So I get the same shape, but here the mean is 0. And then if I selected this to predict, I look again at the future, but the mean. So maybe the future with respect to this one look like this, no problem. I also demean that, but using the old mean, just the mean of this data. So this remain unchanged. Here's 0. And then in order to predict, of course, here I also have the mean. I will add the mean to the predicted values. But in this case, I will add this mean, not this mean. So to get the real data, I will go from this one to this one. But instead of adding its own mean, I will add this mean. So I get the right level, okay? And as I told you, you can either take off and add, or you can divide and multiply. You have these choices. This is a brilliant way to solve the problem not using the differences. Of course, you can still use the differences. If I well remember, the only problem with the code these people wrote in R, the package they wrote in R, is that they don't allow you to put other regressors. That's the stupid part. It would be nice to have also other regressors. But anyway, you can adapt any KNN algorithm to do the same. You have to work a little bit more. And in that case, you could add your regressors as well. Is that clear? I know it's more easier done than explained, but let's just maybe do an example of this, just to show you that this sort of to be the problem. For example, time series like the air passengers in this case are just well predicted. For example. Okay, the package it's called wait, maybe I don't have it installed. I have it on the other computer. It's a long name, but it has KNN inside. Time series forecasting KNN. No, it's this one, I think. Time series forecasting with KNN. Yes, FKNN. So so this is the function to go. So here's this also the paper. So KNN forecasting is here. So here you have the time series. So this is the forecast horizon. The legs is the number of past information to use. And then you can specify more than 1K. So it will try more than 1K. And then again, you see here you can pick two type of forecasting methods. One is recursive. So actually recursive means that it just uses one step ahead prediction and then substitute the prediction inside that instead of the real data. But then MIMO is multiple input, multiple output. So exactly what I described to you that KNN can do. And it's usually better. And I think, well, this is probably newer. Well, this is the how to summarize the values of the forecast from the various specimen, okay, that we selected. You can use the mean, you can use the median. Weighted is kind of new, it was not there. I'm not sure what it does. Probably it's based on the, yeah, it's probably based on the distance. Usually you can, of course, you can either do the mean or the median of the samples you selected, but you could weight this median according to how far away that single sample is to your specimen, okay? Or the query, if you want to call it the query, okay? So it's like a moving a weighted mean. But then you have this that I talked to you about. It calls the transform. You can additive means that you're taking off this kind of trend and then you add it back. It's just a trend, a local trend in some way. Multiplicative, you divide by the trend or nothing. In that case, you have like the standard KNN.
The longer and then always something.
I guess I would say yes. The only, yeah, the mean, yeah, we get. Yeah, I think so. We might try. Yeah, in principle, I would say yes. Okay, let's try just to give a try to this one, and then we can stop. And next time we'll be working on with more methods on a more involved time series, which is the hourly load time series. So let's just use this function. So forecast KNN and casting. So the time series is air passengers. So H, maybe 1 year. We can do 1 year ahead. How many lags? I would use at least 12 lags because we have to include the seasonality. I mean, the whole year, the shape of the whole year is 12 months. So of course it would be not a good choice just to pick maybe the last 3 observations because we have this shape of the seasonality. So here, of course, it's recommended that you have at least the whole seasonality shape. Otherwise, it's hard to learn from the seasonality. You can try. Well, K, okay, it will try 3 different, 3, 5, 7. Okay, fine, try those. And I would use the prediction MIMO. We can also then also compare with the recursive, but MIMO should do better. We can, yeah, we can use either the mean or the median. Of course, the mean would be more in the spirit of minimizing the square loss function. So maybe let's just leave the mean. And what about the transform? I would use the multiplicative. Probably just can write multi and we'll do. What's the problem here? Sorry, 1 through 12. Okay, let's see how the output looks like. Here's some information. Yeah, we could have, maybe let's just, as we usually do, let's just pass the first 11 years and just leave the last one to predict. So I would say from 1 to 132, right? And then we compare the future forecast. I'm not sure, I'm not using this very often, so. Okay, what about summary? Well, actually here we have the forecast. Yeah, of course it generate the forecast. We already said what kind of forecast we want, so. And let's see. I think there's an auto plot or something. No, I've seen something like that. Sorry, I didn't think to show you this, and then I did it. So here's a plot. Okay, this is it. So the time series and of course the forecast, which seem to be pretty good. Maybe we can just add the so the X would be from 133 to 144. And then we have our passengers again from 133 to 144. Maybe we just use a blue. So we can, and actually these forecasts are excellent. Look at that. Really good. Okay. It just picked up probably 3 of these years. I'm not sure how it's using the various 3, 5, 7. One has to read the help because we actually chose different sets of k's. So we have three k equal to 3, 5, and 7. I'm not sure how it's using all of them. If it maybe does an ensemble for it, I'm not sure. But anyway, whatever it does for this very simple time series, it's worked great. But I mean, it's to be expected because it's a very regular time series. The only problem here would be the trend, but you know the trend is dealt with in a very intelligent way. Okay. And of course, divided by the trend also solves this problem of the time series being multiplicative, because if you divide instead of, if you take the trend off, of course, the movement due to seasonality are different. You know, are very small at the beginning and very big at the end. But if you divide by the level, in some way you're making all these differences relative to the level, so as the log does. And so you solve the problem also of the logarithmicity or multiplicativity of this time series, okay? So it's very nice. As I told you, the only bad thing about this function and this package is that it does not allow external regressors apart from this. And sometimes they may be useful. So this is good usually for like monthly time series, quarterly time series. Yeah, I would say we stop here. Just maybe you can understand yourself by the help how it's using more than one value of the k. I didn't remember there was a possible multiple selection of the k. Here, the forecasting is an average. So it's a kind of model ensemble forecasting. So you're doing forecast using k equal to 3, 5, and 7, and then you just take the average of these predictions. So yeah, today we have abbiamo solo fino all:1:30 giusto oggi. Okay, so we stop here. I try to go on with these notes and put it on the e-learning really quickly, hopefully. The problem is that, as you probably noticed, these things are not complex. I mean, anybody of you, I think, if you start just thinking about trends, about steps ahead predictions, you may come up with the same conclusion that I showed you. I mean, it's easier if I tell it to you, but I'm sure if you reason about these problems, you could come up with the same conclusion. But you don't find those things in any book. It's really strange. I try to look for like machine learning for forecasting books. There are not many of these. There are a lot about computer science that is more about telling you which software, which function you should use, but not really about reasoning. I mean, at the end of the day, we did most of the reasoning just by looking at that y is equal to f of x, okay? So, and then reasoning about how these algorithms are able to reproduce, data outside the training sample. They're really, I would say, not complex things, but they're not written anywhere, and that's really incredible. You can, I try to ask Jamie or the other artificial intelligence to write notes about that. They're just bad because there's no material, so they have nothing. They have nothing to copy from. So, and that's strange. But anyway, that's why I'm trying at least to do some notes, and maybe if I have time some days, or we'll do another books about forecasting using machine learning, which is really not about machine learning, but it's really about using algorithms for forecasting of that type of non-parametric forecasting. So, okay, let's stop here. If there are no questions, of course.